Hi, today I'm going to be talking about the fifth tutorial of the VARS-TOOL package. This tutorial covers time varying and time aggregate sensitivity analysis with VARS. In this exercise, we will be covering sensitivity analysis of the HBV-SASK model with time series outputs. An example research question for needing to use the time varying and time aggregate version of VARS is: suppose you have a hydrologic model with several parameters, each defined to be in a given range. This model runs on a long time period, which includes different types of hydro-climatic conditions such as dry and wet spells, and estimates different flux or state variables over time. How does the sensitivity of a flux or state variable to the different parameters change over time under different hydro-climatic conditions? So now, to run the exercise, we need to first import the important libraries such as TS-VARS and the model class. To do this, we press Shift-Enter. Now we introduce the model. To do this, we define a function of interest in sensitivity analysis. Here, the following function runs the HBV-SASK model and returns a time series of model responses. The output of the model here could be the time series of a flux or state variable over a given time period. Again, I will press Shift-Enter. Now we wrap the function of interest with the model class as shown here. Now we can run our wrapped function with an arbitrary input and check the model response to make sure that it's working correctly. And as you can see here, we get a time series output of HBV-SASK, and it appears to be working correctly. Now we create a TS-VARS experiment and set its attributes according to the table below. I will pause for a few seconds so that you can read all the attributes and understand what they do correctly. Now we define the experiment. The most important variable that I should mention is the parameters variable. This is a dictionary with the keys being the parameter name and the values being the lower bound and upper bound of the parameters. The rest can be inputted as desired. Now I will run the program. Now that the TS-VARS experiment is done running, we can see that the loading bars are complete. Now we can check out the results. For the time varying sensitivities, similar to VARS, TS-VARS generates all the sensitivity indices including IVARS, Sobel total order effect, the Morse elementary effect, but unlike VARS that generates sensitivity indices for a single model output, TS-VARS does so for the time series of model outputs. The following cells look at IVARS 50, the total variogram effect, but the user has the option to use other indices as already shown for VARS. For IVARS 50, the result will be the table where each row represents a modeling time step and each column represents a model parameter. This table is called the Generalized Global Sensitivity Matrix. Let's take a look. Here we can see the output with the parameters at the top and the time series steps at the left. Now we can plot the results. So as we can see for these few select parameters, the sensitivity at different time steps changes pretty drastically, and this could be important information to know depending on the model you are using. We can also look at time aggregate sensitivities. The time aggregate sensitivity indices are the average over all of the time steps for each parameter. Here is the plot of the time aggregate sensitivity analysis. The second level of aggregation, the most compact form, takes the mean of the time series of sensitivity index over the simulation time period for each individual parameter. The table that I'm about to show you shows the time aggregate IVARS for all the scale ranges of interest. Now we can choose a scale range and plot the respective time aggregate sensitivity indices for all the parameters in linear and log scales. Here in the regular plot, you can see that TT is definitely the most influential parameter, but when you look in the log scale, you can better differentiate the other parameters and make a good assumption on how sensitive you think they are. For further results, we can look at the time normalization of the sensitivities. When investigating time aggregate and time varying sensitivity indices as shown above, we have treated each individual time step as being of equal importance. However, during some time steps, the response of a model may exhibit more variability than during other time steps, reflecting the dynamics of the model and, importantly, the strength of its forcings. In such cases, the behavior of the more dynamically active time steps may, when summarized into a single time-aggregate sensitivity index, obscure the information contained in less active time steps. For some purposes, therefore, it may be desirable to adjust the weights assigned to different time steps to achieve a more desirable balance. Here we can investigate this. Here we can see in this plot that the values are between 0 and 1, and that the results are more uniform. Here we can see a plot of the time-varying sensitivity analysis normalized at each time step. Now we can look at normalized time-aggregate sensitivities. We will plot the cumulative frequency distributions of the time-normalized time series of sensitivity index for each individual parameter. The distributions that are more extended to the right correspond to parameters that are more strongly influential. We can compare this plot with a similar plot above before time normalization. As we see here, now we can look at the other plot. As you can see, the plot is a little different than how it was before, and we can get a better view of what is happening. Now, the table below shows the time-normalized time-aggregate I-VARS for all scale ranges of interest. Now we can choose a scale. Here we will choose 0.5, and we can look at the plots. Here we can see a better view of what is happening, and now we can see that TT and PM are both strongly influential. Again, we can see the log scale to better differentiate the results. That is it for tutorial 5. Thanks for watching.